Okay, hi everybody. It is lecture number lucky 7. This is the seventh lecture of the weather portion of 8ER 110DE. Lots of numbers and letters there. And we did have some rain over the weekend. It was record rainfall in places like Hanford and Fresno. They had record rainfall there. You can see the snow up in the high Sierra. It's still there. All a good sign to see snow in the high Sierra. We love that because we need the snow up there because it is our time-released water source or resource for the summertime when it never rains. Okay, so that's good. Anyway, we'll take a look at the weather here. It looks like it's completely clear all the way down to San Diego and beyond. In fact, let's just take a look at weather observations. While we're at it, there's a big severe storm outbreak about to happen in Oklahoma and parts of Kansas. They have actually got here. Let me show you. They've got a high risk. This purple right here, that is very rare. It only happens maybe once or twice a year to have a high risk of severe thunderstorms. And they're actually talking about a regional outbreak of severe weather, multiple intense long track tornadoes, as well as very large hail. Severe storm gusts is expected over this area right here. So that's almost up to Oklahoma City. Not quite. Let's see. Is it? Let's see. Well, no, wait, that is Oklahoma City. Yes, I take that back. It does come into Oklahoma City there, over toward Stillwater and Fort Sill, Gage, not quite Gage, up to the Wichita area. So a high risk of severe weather. Here's the chance for tornadoes. You can see it's there. Wind is a little bit more to the north and east, and hail is all over the place. Yeah, whenever I go storm chasing, I may or may not see a funnel cloud, but I always see hail. All right, we're going to come back here. No hail expected in California, really anywhere today. And the weather is great. Let's see, we're at 64 degrees in Bakersfield. It's 73 at Camarillo. Up in the high country, we're in the 60s right now. Let's see what the weather's like where Barbara lives by going to, where is it here? Mezzo. We'll go to Mezzo. I always turn on the dew point because knowing the temperature without the dew point is just not enough. So here we go. Let's see. Fillmore. 69 degrees, and you had a low this morning of 42. Kind of chilly. Did you use the heater this morning?
Didn't use the heater, but it was chilly.
It was chilly. It'll be chilly again tonight, too. So great weather, just invigorating, happy to be alive kind of weather. Kind of windy here in the San Gabriel Mountains. There's a gust of 39, been up to 47 earlier. So it's some very nice weather in the wake of what had been a weather system. And that same weather system is the one pushing now into the middle of the country here with an outbreak of severe thunderstorms expected. That's the same system. Let's look at it here in mid-level water vapor imagery. You can see the winds coming across here and all of this yellow, and you can see some gravity waves there, just meaning a lot of wind is involved. And so right about here, right where the dry line is, and let's see, where is that dry line? Let's look at the dry line. Let's come over here and look at the dry line. So the dew points in Childress, there's a 64 degree dew point. Abilene, 71 steamy degree dew point. But over here in Big Spring, a 43 dew point. And Midland, a 34 dew point. And Wink, only a 20 degree dew point. And it just goes down. Here's Van Horn at 17 and Marfa 10. So it gets really dry, really fast. And up here, where all the action is going to be, goes from a 64 degree dew point in Childress to looks like a 25 degree dew point in Clovis and 19 degree dew point in Level Land. And let's see where else. So there's just a huge boundary which is taking place right here. Look up here. So we're going from a 66 degree dew point with 700 overcast, a little bit of light rain shower activity at Eisenhower Airport in Wichita, to a dew point of 12 over here in Syracuse, western Kansas. So, and even look at this, we got dew points in the single numbers here. Any below zero? Let's look below zero. Got down to 1 for a dew point here at Westcliff. So very dry, very strong winds gusting to 43. By the way, you see this little gust right here. It says G43 upside down. I have complained about that. because there's a way that the aviationweather.gov, they can switch that so that whenever the wind direction is from that direction, this is right side up. They'll say G43, not an upside down. And it's not that hard. But anyway, we'll see if they do anything about that. Anyway, so a lot of action taking place over here. Very low pressures. Let's see, the altimeter setting at Dodge City down to 2, 9, or 4, 8, and falling, I'm sure, even lower up here. And even lower the farther north we get. How low does it get? 2, 9, or 1, 3. So here's a 2, 9, or 1, 3. Rapid City, 2, 9, or 1, 5. Rapid City right now, 2, 9, or 1, 5 with a gusty south wind. So there's just a lot of action about ready to take place over there. So it'll be great. All right, let's take a look at our weather here, though, which is going to be simple dimple, as we say. So we'll go back 12 hours just to make it fun. And we will modify by expanding it. We'll go ahead and take a look at the Taft and go. All right. So Bakersfield, no problema. It's clear and good visibility. Light winds, a great day to go fly. Go fly today if you possibly can. Winds have been calm for most of the morning there. Winds this afternoon will be 310 at 8, and we're going to be basically clear. Just a few high cirrus clouds, maybe. And then in Oxnard, do we have any May gray? No, we don't. It's nothing but clear skies. Winds 270 at 11. Good weather. The same temperature there as it is in Bakersfield. Pretty much the same forecast, too. No significant winds, clear skies. This is the kind of weather we like to learn how to fly. All right, in San Diego, well, there was a little bit, 2,500 few, but otherwise a very nice afternoon. And we do have a ceiling coming up for 10Z later on tonight in the San Diego area. And just before that, there might temporarily be a little bit of something from about 11 o'clock on. But it only lasts for a few hours. We'll be back to VFR 1800 scattered by about 16Z. And yeah, no low clouds in Phoenix. It's going to be perfect there. Nothing but clear skies with diurnal winds. That means that the afternoon winds are out of the west. The late night going into the early morning winds will be out of the east and very, very light. So it's all good all the time. As far as, let's take a look at the global forecast system. We're going to look, we don't want that. We want to look at the actual surface observations and surface forecast. I mean, so here it is. Here's the big picture. That's a little bit too big. Let's make it national. Come down to the national scale. Okay, so here we go. And here's time in the upper left-hand corner. We go through today. Let's see. Oh, yeah, so big storms develop. Well, you know, it doesn't look like it's that big of a deal, quite honestly. If you look at the models, it just doesn't show that. It shows some storms, sure, but I mean, it doesn't show like a crazy outbreak as the Storm Prediction Center is saying. We go all the way now into Friday. By the way, the temperatures are going to really bounce back. We're going to be looking at some pretty hot temperatures by Friday and Saturday. In the Bakersfield area, we'll be up into the 90s. It's not going to hit triple digits yet, but you know, when it hits the 90s in the interior, that just flips the switch on for low clouds and fog along the coast. And so that's most likely what's going to happen. We go into the future. Looks like a big low pressure system moving across the southeast with some big thunderstorms in Georgia and Florida. That will be about a week from today. And then it's kind of cool in the east, probably hot in the west, and another round of thunderstorms. Let me look at the HRRR, which is the high resolution rapid refresh. We're going to go ahead and look at the local. We'll come right down here to Oklahoma just to see what it says about thunderstorms there. Now I'm a little bit curious to see if we're going to get this big thunderstorm outbreak, and it doesn't really. Is this correct? Let me see here. This is 10 a.m. Okay, so we'll go into the afternoon. It really doesn't show anything. This is somewhat remarkable. So here, I'm looking at the time up here. There's Monday, 1 p.m. Central Time. Now we go, okay, so there are some thunderstorms there. We do see something in the Enid area. This is 8 p.m. tonight, but I don't see what I expected. If there is a high risk of severe thunderstorms with long track tornadoes, I would have expected to see a little bit more than this for 8 o'clock tonight. And I will say this, that the Storm Prediction Center, these people know what they're doing. They've got decades of experience, and I do trust them. This forecast was put out by a guy named Smith. I don't know the Smith guy. If it was Moore here, Moore I do know. But if John Hart had put it out, then I would really trust it. So we'll see. We'll see what happens. I'm sure that there are convective models that are saying that there's going to be a lot of bad weather there. But that is a little bit different. That is not what I expected. That does not, it is incongruent to see high risk of severe thunderstorms, the purple category, and then come to the HRRR here and to see what looks like a few showers maybe. That's just not what right there. There's nothing at all. Interesting. All right, let me look at one more thing here, because now I'm really curious. Let me go to the severe. We'll take a look at, let's see, we'll take a look at the surface-based CAPE. So here it is. We're going to go into the future here, and there is a lot of CAPE. Oh, a lot of CAPE right there. Okay, and these winds that you see right here, these are called the crossover winds. So the surface level is red. Then we go up to 850 millibars, about 5,000 feet. That's blue. And then we go up to black, which is 500 millibars. So you would expect to see veering winds. We've talked a lot about this, in fact. This is the favorable vertical wind profile. And we do have somewhat of a favorable vertical wind profile there, because we're going from the red to the blue to the black. It should be shifting clockwise, like you see right here, going from southeast to kind of southwest to a strong. So that's all good. And here we have 50 knots up here, but still, see, we got about, let's see, how much CAPE is that? So this is, let's come over here and look at this again. Stand by to here, right about to here, right there. So we got kind of white. What is that? That looks like almost 5,000 CAPE. Oh, there it is. Just put the cursor on it. Okay, so it's almost 5,000, which is a lot of CAPE. Okay. One other thing we can do, by the way, is we can look at soundings. So let's take a look at the Oklahoma City sounding. Here is the sounding, and this is for right now, and this shows what's known as a cap, not to be confused with a CAPE, which has an E on it. This is a cap, which means that there is an inversion and the temperature goes way up. It goes from 14 Celsius to 17 Celsius, going from 4,900 feet to about 8,000 feet. So this is a cap. So this is very stable. So this is going to hold back all of the heat of the day and until it just explodes. And I think that is why the Storm Prediction Center severe storm forecasters are forecasting what they are. So here, currently, you can see the CAPE right up here at the upper right is the 2970. If we go to 00Z tonight, it goes up to 4,400, and that cap is pretty much gone. It's still kind of there, but it's not as big a deal as it was. Let's go to Oklahoma City just a little bit later. We'll go to 1Z. That's the neat thing about this sounding, the RUC sounding. RUC stands for Rapid Update Cycle, so it updates every hour. See what it does here. Okay, so we're getting rid of the cap, and then if we go a little deeper, let's go to 3Z. Okay, so 3Z, that will be into the, well, it looks like the cap kind of comes back, and we still have a lot of CAPE up here. So anyway, we will see what happens with this big potential thunderstorm outbreak day. It'll be rather interesting. So I'm going to certainly be watching. Let's see, here we have some watches. Here's a watch right here. Oh my goodness, this is a particularly dangerous situation. Notice what it says. Okay, so this is a particularly dangerous situation. Explosive thunderstorm development is forecast this afternoon along and east of a north to south oriented dry line. Well, we saw the dry line. See what else it says here. This was put out by Smith. Okay. All right, so we're talking about tornadoes and a few severe thunderstorms with hail up to 4 inches in diameter, extreme turbulence, surface wind gusts to 65, and cumulonimbus stops to 50,000 feet. The mean storm vector is from 240 at 35. All right, this is a particularly dangerous situation. And here's the area right here. It includes Oklahoma City, Clinton, Altus, not quite Childress, all the way up to Wichita. So this, Dodge City too. So right along Vance Air Force Base in Enid, Oklahoma. So this should be a very interesting day. This is tornado watch number 189, and it has a high, that's purple, likelihood of tornadoes, EF2 tornadoes or above. That would be severe, violent tornadoes, severe wind high, and only a moderate risk of 65 knot plus. But everything else is in the purple zone. Wow. Wow, wow, wow. Let's see, is there any other? I think there's one other. Up here, there's another tornado watch. This is not a particularly dangerous one, but still a tornado watch. So we'll see what happens there. And further to the north, I thought I saw in blue here, here's a severe thunderstorm watch. So it'll be an interesting afternoon. I will be spending my time watching that. All right, how about our weather? Let's get back to what's going on here. We can go ahead and do this, and we're going to go to something else. What are we going to look at here? Let's look at the 500 millibar pattern. And here is the 500 millibar pattern. We don't want that. We want this. Okay. So here, and you can kind of see where California is here. This is a different vendor. This is the College of DuPage. You can see a low pressure system over, this is the same storm, by the way, which is causing the bad weather in the high risk area there over Oklahoma, Kansas. It's the same system that came through here. It gave us rain and some gusty winds on Saturday night and Sunday. It's the same system. And so it kind of winds up over here, but you'll notice it sort of bounces back. Watch this. So here it's coming back into Nevada and Utah right there. And then it kind of hangs out just a little bit. It's like chilling, so to speak, here across the four corners. Now, in this case, time is in the upper right-hand corner. So this is Friday at 21Z. And then it begins to move out and high pressure begins to move in. Now, what's this? We have something down to the southwest. It is coming in. This is a low pressure system here. The colors, by the way, are isotax. That means that they are lines of equal wind speed. So we do have some yellow here. It's in the 70 knot range. There's 675 right there. So we're going to go, and it looks like it comes up right over us there. And this would be for May 16th. So that is a week from Thursday, according to this. And then it continues to kind of hang out. Now, there's a rule of thumb. The rule of thumb is the 570 line right here, the 5700, which means 5,700 meters above sea level. That is the 500 millibar level. If you were to go in a balloon and go 5,700 meters above sea level and look at your barometer, it would say 500 millibars. In fact, it would say 500 millibars everywhere. Way down here over southern Baja, you'd have to go all the way up to 5,940 meters before it would say 500 millibars. So that's what these numbers mean. And there's a rain, no rain line for the West Coast, and that is the 5,700 line. Now, normally they just drop off the last zero, so we call this the 570 line. So the 570 line has to go south of us for us to get rain, and it doesn't look like it does. Wait a minute, here comes a low pressure system. And let me see, and it goes all the way out to 384 hours, which is as far as it goes. And here's the 570 line there, and it does come right down to us. So at the very end of the 12Z run, it looks like we may have a chance for some rain if there's moisture involved. Let's go ahead and just kind of look at the local pattern here. We'll go ahead and look at the local pattern, and we'll zoom out so we can come over here and do this. We're going to do precipitation and that. Okay. So we go all the way out, and it doesn't look like a whole lot of moisture there, just a little bit. And we're going to come out to the beginning here. It looks like it's windy in the Kern County Mountains. And we do get to what may be an easterly flow here. So here is something to look at if you're curious when it's going to hit 100 degrees for the first time. And by the way, I do have a contest on the TV station I work at. You can win $1,000 if you guess right down to the minute or close to it when it'll first hit 100 degrees at Meadowsfield. It's called the Hot Times Contest. Go to Channel 29, read all about it. But anyway, here you can see we have a trough. This is a low pressure, an elongated area of low pressure that actually moves from the east to the west. So here we have this area of colder air moving into the middle of the country, and then it develops this lee side trough right here. And you can see that this is the axis of the trough right here. If we were to look at the 850 millibar winds and temperatures, let's see here. You can see the winds and temperatures become easterly. And whenever there's an easterly component, like right here, you can see all these easterly winds, easterly all the way down to San Diego. In fact, it's easterly everywhere. If you get an easterly wind like that, that will cause warming. That will cause a Santa Ana effect down here, even though it's not real strong. It's not going to be a strong wind, but it is going to be an easterly wind. So once we get into Friday, we're talking pretty warm temperatures. And it looks like that'll continue for a while. These are some very warm temperatures here. Like here, let's see, the 850 millibar temperature is 26 degrees, 27 degrees, and that's at 5,000 feet. So if that was to happen here in Bakersfield, we would be over 100 degrees. Let's see if that does happen. I don't really see it, don't see it, don't see it. Well, maybe here, let's look, right? Let's go back, right? There, that looks like the warmest day. That would be May 15th, which is a Wednesday. And the temperature here is 20. It really needs to be 24, 25 before we start forecasting 100 degrees. But anyway, it's going to be kind of hot. Hey, I know. Let's take a look at the models and see what they say. Here's what the global forecast system says for Bakersfield, at least. It has highs tomorrow, 77, and we're finally up to 82 after that. Right now, we're in the 60s outside. It just feels great. But look at this, 91, 92. Here's 93 degrees for Sunday, 92. So definitely warmer. And of course, we always compare that to our good friends, the national blend of models, to see what it says. And we'll go out into the extended realm. We'll do this. We'll do Oxnard. We'll do San Diego. And we'll do Phoenix. Yeah, let's see if Phoenix hits 100 degrees. And go. And here it comes. So here's Bakersfield. And like the other model, it goes up into the low to mid 90s. So that would be 94 degrees, and that would be this coming Sunday. So a very hot weekend coming up. Chance for precipitations there. Here's the sky coverage. And this is in percentage. It doesn't even get up to 10%. So it's going to be very, very sunny and dry. Phoenix, let's see what we got here. Oh, there's 100 degrees right there. So that's 101 degrees. And here's 99 degrees. That's next Sunday. So that's close enough. It might hit 100. Let's see. No precipitation, completely dry. We'll go to the next featured location, which is San Diego. And temperatures there will be 69, 70, 70, 72. Ah, perfect. It's like you're in California or something. It's perfect weather there. But will there be clouds? And so now we start looking at that. There's 57%. 50, so that's more than half the sky covered with clouds pretty much every day in the morning. So there will be low clouds in San Diego. Finally, we're going to go to Oxnard, our good friends there. And let's see, temperatures 60, 70, 60, 60, 60. Any clouds? Let's see, clouds. Starting on Thursday, we start talking clouds in the morning. No clouds, though, on Friday and Saturday. I bet that's that easterly wind. Then clouds come back on
Marine layer.
Monday. Say again?
Marine layer.
The marine layer. Yeah, we're going to get a marine layer probably by Thursday. I could look at one other thing here. Let's look at this, and that will probably give us a hint. So we're going to come down to Oxnard. Where's Oxnard? Oxnard's right here. All right, so here's Oxnard right here. And so let's see if there are any ceilings on here. And there are, well, wait, there is at the very end, there's a 900-foot ceiling right there. And that would be for May the 9th, which is, let's see, that'll be Thursday. Thursday morning, yes. Okay, so Thursday morning, there'll be a little bit of cloud cover there. And that's the way it's looking. Let's see here, Bakersfield. Where was San Diego? Let's look at San Diego. San Diego's right here. Okay, here's San Diego and ceiling. Yeah, they have consistent ceilings of 1,500, 1,300, there's 2,700. So marginal VFR ceilings. And then the next morning it's 1,000 feet, there's 1,100. And so we do have all of that. But good visibility pretty much throughout. And that is the way it's looking. So it's going to be rather interesting. Any questions about anything? Let's see who else on the call. Okay, we have, okay. We have a few that are with us. Anybody have any questions about anything? Everybody's doing pretty well in the course.
Yes, we are.
Yeah, yes, I've been doing a lot of grading, and the grading is all generally good. Okay, so if there are no other questions here, let's just go right to today's topic. Let me go ahead and change this to true color, not false color. Let me look at one other thing here. Okay. Yeah, there's really nothing upstream. Oh, and I do like to look and always see if there's any break in the ice cover. Looks like, oh yeah, here so you can see Lake Manitoba. The southern part is ice-free. The northern part's still pretty solidly stuck in ice. And even this little lake here north of Thunder Bay is a little bit of ice left. And here it is now. What is today? The 6th. So yeah, things beginning to slowly warm up. Oh, and in just a couple of days, it's going to be hurricane season. Let me see if there's anything here hurricane-wise. Hurricane season in the Eastern Pacific begins on the 15th of May. In the Atlantic, of course, it begins on the 1st of June. And let's see if there are any. I haven't looked at any of this. Let's see if this is even working. It may not be. It is. Okay. So we have one little subject area here. It looks like it's just north of Darwin, just south of New Guinea, a little suspect area there, but not too much going on. All right, so pretty good. And space weather, let's see what's going on there. Whoa. Okay, I haven't looked at this yet. Let's see what this looks like. Right up here. Wow. It's an X. It looks like it's an X-class flare. Let's see what it is. What's this here? Mid-latitude auroras in Europe. Let's check it out here. Let's see what we got. So we're going to come down here to look at this and see what it shows. Okay, oh boy. So this is an X class. So solar flares, which is the GOES X-rays, how we determine that, come in several different flavors, A, B, C, and then M for some reason, and then X. So you can see right here, it was a pretty strong explosion. And there we can look at it on the coronagraph. Let's see if that goes back to, when was that? That was the 6th. So we should be able to see it. Let's see. Right, and I guess that was it way up at the top. Okay, and as far as aurora, it looks like we had one little area here of a minor geomagnetic storm. So, all right, so some action. Here it is. We had a strong radiation. I'm sorry, no, it was a radio blackout, not to be confused with radiation. Radiation would be this one right here, radiation storm, none of those. All right, we're going to get right to the topic now, so let's go ahead and do that. So let me come over here and look at this, and this, and this. All right, if you do have any questions about anything we're talking about, please just blurt it out, okay? See if this works. Does it work? Yep. All right, today we're going to be picking up on where we left off last time, which was thunderstorms. We talked about thunderstorms, and there was this neat little thunderstorm recipe where we have instability, we have moisture, we have that favorable vertical wind profile, which we looked at just a moment ago in Oklahoma. Again, this is really kind of strange because the models are not, I guess they are saying that there's going to be the potential for some explosive thunderstorms, but you don't really see it on the HRRR, which is the every hour it updates the high resolution rapid refresh. So we will see. First, we're going to talk about turbulence today, though. So here we go, turbulence. And of course, what causes in-flight turbulence? Anybody know what causes in-flight turbulence? Let's see if we have an idea here.
Wind shear?
Yeah, that would cause it. Yeah, that would be a big cause of it. And there are so many different kinds of turbulence too. The turbulence, well, let's move a little bit further here. How is turbulence categorized? What are the types? There are several different types of turbulence. How is it gauged? How do we determine how intense the turbulence is? And what resources can a pilot can help a pilot avoid turbulence? Because turbulence will happen. It's like bad things will happen to good people and bad people. You know, the rain falls on the good and the bad. So what we have here is this vector, and a vector has magnitude. You know, this is a bigger vector, and it also has direction. You can tell exactly where it is moving right there. When we have this vector and this vector over here, and they interact, then we get chaos. And because of that, we have all of the aspects of Newton's third law. Newton's third law. And well, I won't get into that. So Newton's third law, there are three laws, you know, and the second law, well, the first law deals with everything that is moving just continues to move as it is, and, you know, unless it is acted upon by some other force. And then the second law actually defines what force is, and that is force equals mass times acceleration. But the third one says that if there is some other force that is interacting with the first one, the first mass, that there will be a reaction, and it will be the same magnitude but the opposite direction. So if you have you know, a ball here, and then you have a cue ball, and you hit the ball, you can calculate exactly where and how fast the other ball will go just by using geometry. But that's what happens with these vectors. These vectors of wind or of your plane or of anything, when they come together, especially with two different vectors of wind, the molecules are bumping into each other. And the third law of Newton is being invoked over and over and over. And so we have chaos. Instead of laminar smooth flow, we have chaotic flow. And there it is. In fact, I just said all that. So I should have gone to the next slide. So the sharper the difference is, the greater the turbulence will be. It's just that simple. So let's look at several different types of turbulence. And these are types, not intensities. The first is called convective turbulence. This is the first one. Now, convective turbulence is turbulence that is caused by these little vertical airs of parcels of air, which is less dense than the air right around it. That's why they're rising, because there is a vertical density gradient. And so these little pockets of warmer air being less dense will rise, just like a hot air balloon. And so they cause turbulence, because you're going this way and it's going this way. And so it's sort of like a speed bump. You know, there's a speed bump there, and you hit the bump, and that causes a lot of Newtonian third law reaction. If you hit it really fast, then you will do some damage. If you just hit it really slow, then you'll just sort of go over it and everything will be fine. But anyway,
Is that what we call thermals?
Yes, that is exactly right. Those are thermals. Some people call it lifty thermals. So we have, just vertical rising air. If you're going horizontally and those parcels are going vertically, then there will be a little bit of vector interaction right there. And so you'll have some turbulence. The rule of thumb is, if you want to avoid convective turbulence, just simply fly above the cumulus clouds. Of course, there have to be cumulus clouds. And if you were flying in, say, Georgia or Missouri or someplace east where there's a lot more humidity, these are cumulus clouds. These puffy little cumulus clouds might be, you know, like at 3,500 feet. You know, it might be scattered at 3,500 feet. But here in the West, where there's just not as much humidity, it's not uncommon to see few at like 10,000 or even 11 or 12,000 in places like Arizona. And that's cumulus clouds. I know it's up in the alto cumulus, mid cloud range, but it is still just regular cumulus clouds. If you fly above these clouds, though, it will be smooth. But that is convective turbulence. And yes, thermals, that's the term. Next, we have the second kind, and this is mechanical turbulence. Now, mechanical turbulence is turbulence that is caused by horizontal wind flow over something other than a smooth ground. Anything at all that sticks up out of the ground, like trees, buildings, signs, anything, that will cause this sort of chaotic effect. So here we go with chaos again. It's chaos. And third law of Newton. So we have molecules bumping into each other, causing an equal and opposite reaction. And so and then this just goes downstream, and we have little vertical eddies, and it's just nothing but trouble. And of course, as you're trying to fly that, you are having to deal with all of this third law of Newton stuff. I have gone on storm chases quite often in the middle of the country, and they have these silos. Here's a silo right here, and then the road is like this, and the wind is blowing, say, from the northwest or something. And then as you go past the silo, there's this downstream effect where the winds shift very, very dramatically, and there's a lot of turbulence there. So that's just another example. That is an example of mechanical turbulence, because we have this big silo which sticks right up out of the ground and causes a disruption to the otherwise laminar smooth flow of air. Now, an extreme example of mechanical turbulence would be the third type, which is orographic turbulence. Now, orographic turbulence is caused by mountains. This word oro means mountains. And then you can see these neat little clouds. These are alto cumulus standing lenticular. The reason they are standing lenticular is because they don't move. The cloud itself forms right here on the windward side, and then it gets big and fat in the middle, and then it tapers down and just goes away on the leeward side there. But the position of the cloud does not change because the thing that caused it, the mountain, does not change. If the mountain were to flow along, then those clouds would also move. And these orographic clouds are a type of gravity wave where we have an up. Something causes the wind to go up, then gravity brings it back down, but then we have this vertical eddy thing going here, and this wave cloud in the top of all of these little eddies. So yeah, it's a kind, orographic is a type or a subtype of mechanical turbulence. Mechanical turbulence is caused by anything that sticks vertically into the airflow. And of course, a mountain sticks vertically into the horizontal wind flow pretty dramatically. So that is a third type of turbulence. There's a fourth type. This is called clear air turbulence, or CAT. And clear air turbulence is turbulence that is caused by synoptic features. Synoptic features. Now, you remember we talked about synoptic weather, the different 100 different kinds of weather. And anything that is considered a synoptic feature is something that you can plot on a map. Low pressure system, cold front, a dry line, an instability line, a trough, anything that can be plotted, or not plotted, can be depicted upon a weather map is a synoptic feature. And it's these synoptic features that can cause generally high-level clear air turbulence. Now, it says clear air, making you think that it has to be clear and free of clouds. That's just not true. Clear air turbulence can certainly happen. As you see in this picture, there can be all sorts of like cirrostratus clouds or just cirrus clouds. It's not uncommon at all to have a clear air turbulence in the vicinity of the polar jet stream. That's a synoptic feature. or the subtropical jet stream. That's a synoptic feature. And with a lot of cirrus up there. So here you are at flight level 330, flying somewhere, flying east, I guess. And there will be a lot of bumpiness because there is the turbulent jet stream right here. Here's the jet stream right here. There's a maximum right there. The winds are 140 knots right there and maybe 100 knots out here. And the winds are blowing this way, and you're just flying right through that. You can expect to see some turbulence. Clear air turbulence. Then there's a fifth kind. This is called wake turbulence. You've all heard of wake turbulence, I'm sure. Wake turbulence is caused by aircraft. It's caused by the entire airfoil and the fact that we have low pressure at the top, high pressure down here because of the shape of the wing, the Venturi effect. Then we have these little vortices that develop here on either side. And they're like little horizontal tornadoes. I mean, they're spinning, just like you would expect. Let's see, these would be spinning this way. These would be spinning this way, you know. And if you or just happen to be flying through one of these, there'll be a lot of chaos. So yeah, wake turbulence is a big thing, not only if you are landing and taking off on parallel runway, certainly then. If you're taking off on this runway, and there's a big jet right here taking off, and the winds are blowing this way, and then you're trying to take off, there might be some wake turbulence on that parallel runway. But you can also have wake turbulence at flight level. You can be at 33,000 feet, and these little vortices, they happen whenever the plane is flying. That means it's not in contact with the ground. And if you're flying at 33,000 feet, you're not in contact with the ground. And so there will be little vortices that will travel behind. I say they're traveling. They're actually existing behind the aircraft, sort of like, in a sense, sort of like contrails. Maybe not quite as far back and as long lasting as some contrails are, but if you can be like a couple of miles behind, and maybe as much as 1,000 feet below. You can be 5 miles behind the thing, behind an aircraft over here. Here's the aircraft, and you're flying over here, and you can just hit a little bit of wake turbulence at flight level. So it does happen. Now, turbulence is measured in basically 4 different versions of intensity. Of course, nil means nothing, but the light turbulence will take place when, let's see if I have anything. I don't. All right, so light turbulence would be a situation where you feel a little bit of effect on your seat belts, your straps, and you definitely feel some percussion, and the aircraft can move vertically, vertically one way or the other. Maybe stop this. Maybe 5 feet or something like that. Not a lot. Not a lot. So generally a single number of feet. The difference between light turbulence and light chop. You've heard the term chop. Chop, you feel the turbulence, you feel the percussion, and if you're trying to walk along, it might in the galley, you might actually feel something, but you do not change altitude. So no change in altitude, no change in altitude for chop. For turbulence, there is a little bit of a change in altitude. Moderate, we're talking tens of feet. Tens, so maybe 30 or even 60 feet, you will go up or down because of this turbulence. And obviously, it'll make it difficult to maneuver, to walk in the back of the aircraft. Drinks might get spilled or something like that. And of course, you can have moderate chop. You can have that too, where you feel it, but you don't really change your altitude. That's the difference between turbulence and chop. Well, chop is a kind of turbulence, but it's a turbulence that doesn't change your altitude. Okay, those are those two. Now we have severe. This will change your altitude hundreds of feet, 200, 300 feet, maybe more. It'll be almost impossible to walk. This would be a situation where you could briefly be weightless, because you have extreme changes in altitude. There is no such thing as severe chop, by the way. Severe chop does not exist. No. You can only have light or moderate chop. And then finally, we get to extreme turbulence, which is just severe, and then you add to it. Extreme turbulence means that you have lost control of your aircraft, and you are tumbling like you're in the dryer. You are just sort of all over the place, and you never want to find yourself in extreme turbulence. Never, never find yourself in extreme turbulence. So you have to avoid these things. You have to mitigate. And extreme turbulence can happen. It happens quite frequently in mountain waves. That's orographic turbulence. You can have extreme turbulence at CAT. You can have that especially over the North Pacific when you have just really, really strong jet streams. There are some jet streams over the North Pacific that I have seen where winds are like nearly 300 knots. That's extreme. But I mean, it's sort of like the high risk, high risk for severe thunderstorms like we're having today is somewhat rare, happens once, maybe twice a year. Turbulence involving a jet stream over the North Pacific where the winds are over 200 knots. That happens like every year. It's somewhat rare. I mean, to get 200 knot winds is pretty amazing, but it does happen. I should check and see if it's happening today. Anyway, so those are the 4 different intensities of turbulence. Now, low-level wind shear is a kind of turbulence. It's not specifically, it's not numbered. Yes, question.
Right. So, you know how like there's different like severities like for turbulence, but it affects planes differently. Like 172 will be different from a 380 from light to, that could be
Absolutely
moderate too. So because of that, that means that plane, like the Airbus 3 whatever, is can withstand more turbulence than a Cessna, correct?
Yeah.
And so in theory, could you remove turbulence in general?
By just making a really big plane?
Yeah, could you like in theory make a really huge plane and just make it so turbulence is basically like nil,
I guess in theory, I don't know that you would ever eliminate turbulence. In fact, I don't think that you would. But yeah, it might be just a little. Yeah, there would be some tangible effect. Yeah, I would say yes. Yes, a really, really big, I don't know, 777 or whatever, or Airbus 380, 800, or like that. Yeah, like a Airbus 380, 800, like Emirates. They fly these huge aircraft, and they are so big that there's just, the thing is that the forces that cause the turbulence have to move mass. That's what work is. Work is force times distance, basically. And but if there's so much mass to move, you need more force to do it, and you have only this much force, this much turbulence. So yeah, the bigger an aircraft is, the less of effect turbulence will have. But I don't want to give you the idea that it's really something that's possible. It is possible, I suppose, but no, turbulence is a very significant, big deal. It's a big hazard.
Okay.
It is probably the most common hazard of all. It's much more common that you're going to have to deal with turbulence than with icing. Even though icing is very, very difficult to get out of if you're in an icing situation. But just in a place like the West Coast where there's not that much moisture, You're not going to have that much icing, but you'll always have turbulence. And it's more likely that you'll find yourself in a turbulent situation than in a thunderstorm, because to avoid thunderstorms. Sometimes turbulence is just so ubiquitous, it's just all over the place, especially when there's a lot of wind. But that is a good point. That is a good point that, yes, within your little Cessna 172, you are more exposed to the dangers of turbulence than some big aircraft would be. Yeah, that's true.
Okay. All right.
Good point. All right, next is low-level wind shear. And by the way, Barbara, if you're on the call, do you want to weigh in on that or not? Maybe she's not there. Okay. So low-level wind shear, we're talking in this case an inversion. So it is cooler down here, like in the morning.
Actually, I didn't come off. I'm sorry, Mouse. I didn't come off mute quite as quickly.
Oh,
Airplanes can change depending on the turbulence that they encounter. It definitely is an effect on the airframe, and you may find that in some cases you'd say that it's more severe turbulence that a larger aircraft would encounter. I'm not sure that's always the case. I can't give you a substantial input on it. Of course, the airliners fly in areas where you have jet stream and you have a lot more clear air turbulence than we would necessarily get at lower altitudes. But there are some things that, a lighter aircraft may not be susceptible to turbulence as a heavier aircraft, largely because of weight and mass. So,
well, you've flown how many different types of aircraft? Heavier ones, bigger ones, lighter ones. Is it your experience that these small aircraft are more susceptible to turbulence than a heavier, bigger aircraft?
I think it depends on the situation.
Okay.
Definitely, but when you get severe turbulence in a light aircraft versus a heavier aircraft, there may be cases where you would get severe turbulence in a heavier aircraft that the lighter aircraft is not. It would still be a good ride, but they're not as susceptible to it. They tend to float more in the air than necessarily the heavier aircraft.
That's true. There's more area. There's more airfoil area on a big aircraft to be affected, I suppose. By
and I think it also depends on the impact, if you will. How sharp the response is.
Mm-hmm.
I can't remember. There's something in the back of my head that's floating around on that. I have to go look. Might be something we could do next term.
Okay.
So, anyway.
All right. Thank you very much, Barbara. Looking here at this other type of turbulence, which really isn't a turbulence in the same way that mechanical and convective and orographic and all that is, but this is just simply a wind shift or wind shear in this case. So you're coming in for a landing. As you can see, the plane's coming down for a landing, and there's a nice headwind here. But once you get below the inversion, well, it all changes. So now the wind is a tailwind, and that sort of thing can happen. So we do have different wind regimes, due to the different thermal environments, which change vertically. Even though you're going, if you go vertically, you expect it to get cooler, but in the morning, that's not always the case. It cools off faster at the ground. And so there will be some low-level wind shear when there are inversions. Just remember this, we're talking inversion right here. And also you can get low-level wind shear when there is like a significant weather system coming in. And you can sometimes get a situation where you'll see it on the TAF. For example, let's say the winds are, we're coming into KBFL, and the winds are, we'll say 120 at 20. Gusting to 28 knots. But then at the end of the TAF, way over at the end, there'll be a wind shear at say 2000, and the winds will be like 180 at 45. So that means that as you go to 2,000 feet, expect really strong southerly wind, probably a lot of turbulence there. Or if you're landing, you have this really strong south wind, and then it's not quite as strong, and it's from a completely different direction once you get down to near the runway. That's a wind shear, low-level wind shear. Here's another kind of wind shear when you have a big thunderstorm up here. Here's a thunderstorm, a lot of rain. If you are taking off into the thunderstorm, well, you have an increasing headwind, and I guess that's good. But then once you get to right below where the rain is falling down, then it's going to be pushing you down to the ground, which is bad in itself. But then if you go a little farther, now you get a tailwind, and you're going to stall. So yeah, wind, that's another kind of wind shear, which is a downdraft or a downdraft or a microburst. Microburst. And there have been quite a few accidents due to this. Of course, you'll know the famous Delta 191 flying into DFW back in 1985. We had a whole thing on that. That was a microburst. So what do? Be prepared. Be prepared to immediately react to aircraft performance changes. Do not attempt to land during severe low-level wind shear. Yeah, and low-level wind shear can be categorized by intensities too. You can have moderate, and you can have severe low-level wind shear. Avoid any interaction with a microburst. If you see a microburst, don't go that way. And finally, if caught in a microburst at low altitude, fly 90 degrees to the outflow until clear of danger. And so if here's the big storm over here, and you are here, then you don't want to fly into the storm. We know that. And you don't want to fly directly away from the storm because there'll be an outflow. It'll cause you to stall. So you fly 90 degrees until clear. You fly 90 degrees to the outflow until clear of danger. And that is the rule for microbursts. Well, that's a taste, so to speak, of turbulence. Now we're going to have a taste of icing, literally. So just like we had a recipe for thunderstorms, and this all looks delicious right here. We're going to, buttercream icing. We're going to go ahead and have the icing recipe. So the icing recipe, we have to have certain ingredients, milk and sugar, perhaps, and flour. But for structural icing, we have certain things. There's an induction icing as well, which deals with carburetors. So aircraft icing is the accumulation of ice from the atmosphere that negatively affects the performance of an aircraft. And I will just say right out at the beginning here that there is no good icing. I've asked the question before to some students that, are there any good hazards? And generally people will say, well, yeah, maybe light turbulence is a good thing because it doesn't really, it's not threatening you with death or anything like that. And it gets your attention, and that's a good thing. But icing, there's just nothing really good. I suppose maybe a trace of icing. So you see that, oh, now I know. Okay, so that's good. But any of the intense versions of any of these things are very, very bad. Structural icing is airfoil deformation. So you're going to change the shape of your wing. You don't want to do that. There's also instrumentation ice. And so ice is gathering on your pitot tube, and you can tell that's a bad thing because now you have bad information. So it's just bad all the way around. It decreases lift, increases drag and weight. Structural icing is never a good thing, any kind. And then there's induction icing, which is carb ice, and that develops due to the Venturi effect cooling, resulting in fuel flow failure. Say that fast 3 times. And it is basically due to the little bit of water which might be in the fuel, which then turns into ice. And it's like cholesterol in the bloodstream. It just simply blocks. And the next thing you know, you have an aircraft stroke, basically, is what it is, or at least for the engine. And there are types of icing, as you've probably heard. Rime is one type. Clear is another, and mix is a little bit of both. So that's the hybrid structural aircraft icing type. You fly through a cloud or precipitation containing any liquid water droplets in a below freezing environment, and the temperature, the outside air temperature is greater than -24. So what are we talking about? First of all, what? I thought water froze at 32 degrees Fahrenheit, 0 degrees Celsius, but it doesn't. The answer is no, it doesn't necessarily. If you have water droplets, liquid water droplets, it is a characteristic, a physical characteristic of water, that if it is just sort of suspended in the atmosphere, it will continue to be liquid water, even though the air temperature is below freezing, unless it touches something, and there's some aerosol or something that it can freeze onto. But if it's just the water in the atmosphere, you have to get below -24. Now, why is -24 important? Because there have been experiments done in labs. This is going way back to the 40s and 50s, 1940s and 1950s, where it turned out that at -24 degrees Celsius, -24 degrees Celsius, half of all of the water was liquid and half was ice. And as the temperature goes colder, go down to -28 or -35 or anything colder than -35, it's like 100% ice. And if you get warmer than -24, so we're up here at -15 and -6 degrees, say, then it is more likely to be liquid. So I like at -15, maybe 75% would be liquid. I don't know that that's the case, but anyway, more is liquid. So there is a sliding scale, and the halfway point, the 50-50 point, is at -24 degrees. So if the air is colder than -24, then the odds are that it will be ice. And if it's ice, well, that's fine. You can fly through ice pellets, or not ice pellets, ice plates. You can fly through snow. You can fly through cirrus clouds, and there's just no problem at all. But if you're flying through liquid, super cooled liquid, and super cooled means that it's just below freezing and still liquid, and it touches any of your structure, this will happen. We're going to see it turn into ice. Of course, in this particular case, this particular picture right here looks like there's been a lot of freezing rain, and that's what that is. So yeah, that's a little bit different, but icing is a big problem. So ice forms in stratiform clouds. That is rime icing, and it is caused by tiny air bubbles. That's what gives it the white color. Little tiny air bubbles are developing. Rime ice. It is a very common type of ice. Then we have clear ice, which is like a glaze right here. It is not white like rime ice because there are no air bubbles in there. It actually freezes a little slower. One of the reasons rime ice is white is because it has tiny air bubbles. Why does it have tiny air bubbles? Because it freezes so quickly. And that's one of the things there. So we have this thick, heavy glaze. That's clear icing. And then we also have a little, and that can happen too, and that's called mixed icing. There are two other kinds of icing, by the way, I should mention. There's the supercooled large droplet icing, which is a kind of clear icing, actually. And that is the worst icing of all. That is the one that will bring an aircraft down, and has. And then there's frost. Frost is just deposition. That is water vapor that goes directly to ice. It does not go through the liquid stage or phase. And so that too can be a big problem. So frost can increase drag and increase weight and decrease the lifting capability of your airfoil by 30 and 40%. So it's a big deal. Icing comes in 4 flavors as well, not 4 flavors, but 4 intensities. But there is no extreme. So this is a lot like turbulence. Remember, there were four. It was light, moderate, severe, and extreme. Well, here we have just replaced light with trace, and then we've gone all the way up to severe. There is no extreme icing. No extreme icing. So trace icing, you just start seeing it. Light icing can be mitigated with anti-icing equipment, which I don't know that there are any anti-icing equipment for structural icing, at least on Cessna 172s. I know there is carb heat, and that will help that situation for induction icing. Moderate icing, you have to have the icing, de-icing equipment on the whole time. And then severe icing, you have to get out of there because you cannot fight severe icing. Here is the symbology for that. This is light icing, moderate icing, and severe icing with the three lines. It's a U. By the way, for turbulence, by the way, it is an upside down V. This is moderate turbulence. Here's severe turbulence, and that's extreme turbulence. And light turbulence is just sort of that little bump. So there are many different resources that you can use on aviationweather.gov to look at the icing forecast. It also gives you freezing levels. You need to know when you are flying above the freezing level. Today, if you were flying at 10 or 12,000 feet, I'm sure you would probably be above the freezing level, but it's completely clear out there, so there is no real icing problem. Plus, we do have SIGMETs that are issued for icing, and they are for severe icing. You'll only see SIGMETs issued for severe icing. In this case, we're up in in Finland, I think it is. So once again, here is just another. We can take a look at some of these in just a moment. I think we will at some of the turbulence and icing events that are taking place across the country. So that is it. Assignment 3, which many of you have already done, and thank you for that. We'll do assignment 3, which is explain the general process of initializing and running a computer weather model, which many of you have done very well. How do thunderstorms form, including their 3 stages, and then finally the 3 primary aviation weather hazards, what they are. And again, many of you have already done that. And then the other thing is study for the quiz. There will be a quiz. By the way, I sent out today the lecture slides for the second half of AER 110 weather. And so you can look at those if you want to. Study for the final. Next time, and by that I mean Wednesday, we will have a review. We'll go through all the stuff that we've learned so far in this intermediate aviation concepts weather part. Okay, so got that.
That final is the 30 question. That's
Yes.
Kansas, correct?
Yes, that's exactly right. And that won't be due until Sunday. So you have until Sunday to do all that. Let's look real quickly here and see if there are any AirMets. We'll go to here. Pardon me. So we're going to go over here and turn off METAR. And we're going to look at, let's see, G AirMets. And this is all IFR conditions. But I can also do turbulence. Let's do high-level turbulence. So we do have some high-level turbulence over here in parts of Colorado. So here is some moderate turbulence from 18 to 44,000 feet. Over here, we have moderate turbulence from 20 to 38,000 feet. That's high-level turbulence. Let's go ahead and turn off the high-level turbulence, and we'll go to low-level turbulence. And we do have low-level turbulence. We'll see what we have here. So from the surface to 18,000 feet over Colorado, looks like moderate turbulence. We'll go way over here to Minnesota, and below 5,000 feet, moderate turbulence. So the AirMets do talk about moderate turbulence. Let's look at icing. Any icing? Any icing? Oh, wow, lots of icing. All right, so up here over Wyoming, the freezing level, 8,000. That's the base, and sometimes it's the surface, and we're going to go all the way up to 20,000, moderate icing. Okay, so this whole area up here, moderate icing. Over here in North Dakota, let's see, the freezing level is 7 to 11,000 feet, and all the way up to 22,000 feet, it's moderate icing. Okay, and over here too, we have some moderate icing over New Jersey from the freezing level, which is 11 to 12,000 feet up to 25,000. That's a pretty high icing over there. All right, so that's icing. Now we're going to go ahead and turn icing off, and now we're going to look just at sigments. Any sigments? I bet there are a bunch of convective sigments. But not only that, we also have some turbulence sigments. So let's look at this one right here. So here is a sigmet. This is sigmet Yankee 7 for Wyoming, Colorado, New Mexico, and it's for occasional severe turbulence between 32 and 43,000 feet due to mountain wave action, reported by multiple aircraft and conditions continuing beyond the end of when a sigmet would normally end. Let's see, do we have any icing? Icing? We can go over the entire world here. See any icing? I don't see any icing anywhere in the world. How about that? No icing anywhere in the world. Okay, well, that's good. No icing. Wait a minute. Here's one over here. All right, this is in Russia. Here is icing. And this would be from the surface to 10,000 feet. The area is moving northeast at 11. It's no change. And it is areas of, let's see, surface to 10,000 feet. Severe icing. Here it is right here. Severe icing forecast, and gives latitudes and longitudes over Siberia. All right, so that's what's happening there. And by the way, if we were to look at, let's see here, at this icing. Okay, so icing. So here is something that you can use. This is a resource. So you can pick a time. We'll pick down here at the bottom, 00Z. We're going to pick a specific altitude, 12,000 feet. At 12,000 feet, so here, it looks like we do have the potential for some icing. And of course, the darker the color, let's see what the legend is here. So here we have the legend. And so this would be moderate to heavy icing right here, according to this computer model. That's at 00Z. If we go to like 6Z, we're going to go to 060. You can see it moved. So this is a computer model for icing, and that's icing. And you go up here to the weather, and you just go to icing. Let's turn that off and go to turbulence, and now it's the same thing. You can pick a, let's go to 36,000 feet, and we're at 36,000. We're going to go at 5Z. I don't know why I picked that time, but I did. So here is the eddy dissipation rate, and that would show some pretty significant turbulence. Oh, look, and it shows the light, medium, or heavy aircraft. You see that? And so this sort of goes into what we were talking about before, so that what would be light turbulence for a heavy aircraft, we're going right here, right there, would be moderate turbulence for a light aircraft. So that's a really good example right there. And then, yeah, so the heavier the aircraft is, the less the eddy dissipation rate will cause turbulence. So there you go. That's exactly what you were talking about, Mitchell. Very good. All right, so that's that. And let's see if there's been any change. I'm just looking to see if there's been any change in that severe weather in the middle of the country. Just real quick, I'm going to look at that and we'll call it a day. Let's go to this. And here. All right, here's the dry line. Big thunderstorms up here. We can go to Mosaic radar and see what's happening. Looks like these thunderstorms are just beginning down here. And this is the area under the gun. Why? Because there's a big cap that is a mid-level area of warm air, which makes it stable. But then at some point the cap is broken, and then all of these thunderstorms are explosive. And we have updrafts of 100 knots or more, and that's what causes the really bad weather. So yeah, let me look at Amarillo, or we'll go to Dodge City. We'll go to Dodge City right here and see what the thunderstorms look like. And there they are. Put them in motion. Just now starting. See if there's any hail. We can go to this and see if there's any red. There's some hail up here. You can see a little bit of red right there. And the storm tops are up to what? So there's some red right here. That would be 46,000 feet. So 46,000 foot tops. A lot of weather going on there. Cool. All right. That's it for today. And I want to thank everybody for watching. And we will go ahead and bring that to an end. Anybody have any questions about anything?
I do. It just came to my mind as we were talking about icing. Um, when hail gets bigger, like to the size of like a baseball or whatnot, is that an indication of how fast the updrafts are, or
Yes.
is that what that is?
Yes, you could make a direct correlation between hail size and updraft. Yeah. In fact, here we can look at, let's go over here and go to this. We're going to go to mesoanalysis. We're going to go over here to the Southern Plains right here. And we can do composite index. We'll look at hail size. Here we go. So, well, actually, it's not as big as I thought. So here, the blue is 3-inch. Normally, we get into the white, which is down here. We have that, but there is a definite correlation between hail size and let's see, and updrafts. Here's the large hail parameter. Let's see. Oh, there's a lot of hail there. That hail is just hailaceous. By the way, here's a violent tornado parameter. Wow, which is all pretty dramatic. Yeah, so I can see where there's going to be some big thunderstorm activity. But again, it didn't show it on the hourly update HRRR, which was very, very unusual. Let me look at one more model here. I just got to do this since we're just talking about it. So let me go to this. We're going to go over to this and this area here and see what it says. Okay, this is the NAM model, and this is a little bit more dramatic, and you can kind of see it shows some big thunderstorms there and moves right through the Oklahoma City area. That's a big thing. And the convective, let's see what we got here. Supercell composite. Okay. Oh, yeah. That's what I would like to see if I was out there storm chasing. I wish I was. Here's a significant tornado parameter. Let's see what it says. It's huge. Wow, getting up into the 10. So that shows that there's going to be, yeah, okay, there's a lot going on. Oh, and updrafts. Let's look at updrafts. Here's the updrafts, and this is where the updrafts are going to be really significant, right along there. Okay, yeah, lots going on. It's going to be kind of an exciting day. I'm looking forward to it. All right, any other questions about anything? All right. Well, everybody have a wonderful day. If you have any questions about anything, just go ahead and email me, and we'll go ahead and look at those. In the meantime, we'll see you on Wednesday, and no other questions. We'll see you then. Bye, everybody.
This isn't a question,
Bye.
but it was just
Thank you.
because of
Oh
something
yeah,
you, it wasn't some. Yeah, this is not a question. It's just something you stated because I typed it in the chat, but I don't think you saw it. And you're talking about de-icing for the Cessna 172, and it was for structurally like the surface, and the only one that I know of technically is ourselves as the pilot. Like we scrape it off, like it says in the POH. Like
oh, okay. Yeah, that's how you get rid of the frost icing.
I guess so. That's
Yeah,
how I was saying. Like that's one of the de-icing for like surfaces. Like that's the only one that I know of officially.
Right. Yeah. Well, there's carb heat too, but as far as structural icing, yeah, you don't have the weeping wings or the boots or any other methods of getting ice off of a Cessna 172.
The airplane is not certified for flight into known icing.
There you go.
Yeah.
That's it. Yeah. Well, that answers that. So stay clear of icing. In fact, yeah, let me see what the, I'm just curious now to know. Let me go over here and check to see what the Bakersfield sounding is, to see what the current temperature is. So we're going to go ahead and look at Bakersfield, okay, BFL, and we're going to look at the latest and see what it says. So right now, the freezing level is right here, right there. Oh, okay, so it's higher than I thought. So here's the 0 line right there, that little red line.
Rosemar Winery and Farm. For hours and location, press
So that's yeah, 11,000 feet.
To make your reservation for wine and food service, press 2. For questions about our wine membership or small party reservations in the tasting room, press
2.
3. For large private events, weddings, and overnight accommodations, press 4. For all other inquiries, press 5.
5 it is. Okay. So here's freezing levels, by the way. And so this is from the River Forecast Center. You can go hour by hour. Let's see. Let's go way out here to like Thursday. So Thursday, you can see the freezing levels way up here at 12,000. Up here, a little bit lower.
I'm not able to take your call, but please leave a message and I will get back
All
to
right,
you.
so enough wine tasting. So we'll see you all next time. Okay?
Cindy, this is Barb Wilkinson again. I got the email, it's my card, and as far as I know, my card is updated in there. Just check